So now that we are in the unit of unbalanced forces, we're going to be looking at very unique scenarios where we care about Newton's second law, right? The unbalanced force is equal to mass times acceleration. So when we think about unbalanced force, it's kind of like somebody is winning the tug of war by a certain amount. So let's say we have an object that's sitting on the ground and it's being pulled. So we've got Fn and we've got Fg. But it's being pulled to the right, let's say, so we've got an applied force to the right, and then maybe just a little bit of friction to the left. We would have an unbalanced force in this scenario because the force of friction and the applied force are not equal. We're assuming that normal and gravity are equal. But the applied force would be winning, right? We'd have a tug of war, and the applied force would definitely be winning to the right. However, in the real world, we don't always see these forces, especially the applied force, being like perfectly to the right. It's kind of a very unique situation that we see that. More often than not, what we see is that that force isn't directly to the right. What we see instead is that maybe it's kind of at an angle. Maybe it's kind of to the right and kind of pointing up a little bit. That's kind of more common than straight to the right or straight to the left. So the question that we're gonna kind of delve into today is like, what do we do when we see a force that's like that? What do we do when we see a force that's not exactly to the right or to the left or up or down? Okay? So let's remind ourselves about vectors. Remember, a vector is a quantity that is represented by an arrow, and it has both magnitude and direction. Now, it's really important to talk about how this direction can be any direction. Before, we've seen our directions as either like north or south or east or west, or right, left, up, down, forward, backward. But that direction can be in any old direction that we want. So I'm going to give you a little example here of a vector that is not just north or south or east or west or right or left, okay? Let's say that you and your friends are going out to lunch during school, and you are going off campus for lunch. You're not going to go to McDonald's, you're going to go to Wendy's. I know most of us go to McDonald's though. So assuming this is a normal COVID time. Well, you're not going to go like straight from the high school to Wendy's. You're going to drive on Monona Drive south. You're going to go south, and then you're going to go east on Flown Road to get to that Wendy's over there. Obviously, we can't drive directly from the high school to Wendy's because there's no roads there, okay? But if we remember our displacement is where you start versus where you end, right? So in this case, where we started was the high school, and we ended at the Wendy's. That's our displacement vector, okay? We ended up southeast of where we started. Okay, so that's our displacement, and it's not in one direction. I literally just said that we went south and then we went east. So our displacement is southeast of where we started. That's two different directions that we have to worry about. We went south on Monona Drive and then east on Flown. Okay, so what do we do when we see that displacement, when we see that vector in two different directions? Okay, the thing about directions is we always have to treat them independent of one another. So up and down is independent of left and right. And that's really what we're kind of gonna do today, okay? So when we think about this displacement, well, it has components. It has a component that's in the south direction. It has a component that's in the east direction. Okay, you might already see this, but that's our hypotenuse of our little triangle here. Our displacement is the hypotenuse of our south and east. Before you freak out about triangle trig, it's going to be okay. Let me just kind of break down what I'm talking about here. So as I just said, the delta x, our displacement, it has components in the south and the east directions. Okay, so what we're going to be talking about today is vector components. A vector component, it's basically just a part, right? A component is a part of something. So vector components are parts of a vector that point in the, quote, standard directions. And by standard, we mean north, south, east, west. We mean up, down. We mean left, right. or forwards, backwards. Okay, none of this southeast, northwest business. So this vector component, it tells us how much of the vector is pointing down, how much of the vector is pointing to the right, left, or up. So this is a really handy thing for us to determine how much of those vectors are pointing in those standard directions. Okay, so as I said before, we have that south component, that east component, which makes up our little right triangle, so we are going to be using right triangle trig. So when we're looking for that hypotenuse, okay, or when we're given our hypotenuse, we're going to be able to split it up into the components because we'll have enough information to split it up into the components. And again, we want those components because they tell us information that's in those standard directions which we like, up, down, and left and right. So this method, this vector component thing, can apply to any vector. So we've talked about a lot of vectors in this class, like displacement, velocity, acceleration, and just now force. So the example we're going to do is with forces, but come next unit, we're actually going to be delving into vector components with velocities. And it's going to be the same thing. This component thing applies to any arrow, right? Any vector. So we're going to do an example with forces right now to kind of break down this vector component stuff that I'm talking about. So here's my example. Let's say you're running through the airport and you're pulling on your suitcase, okay? When you pull on your suitcase, you're not really pulling straight to the right, like the way that you're running, and you're not pulling straight up. You're pulling kind of to the right and up at the same time. So you could call that an applied force, or you can call that a tension force. Why don't we just call it applied, because you are applying a force on that suitcase, so you're applying your force up and to the right. So what we're going to do is break down that force into its right component and its up component. How much are we pulling it to the right? How much are we pulling it up? Again, because that information is easier for us to digest than this vector that's at an angle. So what I'm going to do is draw this force by itself over here on the right to be able to break it down into its right component and its up component. So we have the applied force up at an angle. There it is. And usually we care about, it's called this angle above the horizontal. So right now it's kind of pointing up and to the right. So if we consider the horizontal, that's like the ground, right? It's perfectly flat there. So the angle that we care about is the angle above that horizontal. So that symbol that I just drew, that's the symbol for an angle. Let me write it up here. It's the symbol for an angle. It's a theta, a Greek letter theta. You might have seen it drawn like this instead. I draw mine a little fancy. But that's just, it just means an angle. So any old angle, it could be 30 degrees, it could be 75 degrees, whatever angle you want, okay? And we call that the angle above the horizontal. That's usually the angle that we consider, just because it's easy for us to look at, I guess. So what we've got here, again, I said that this applied force, we are pulling to the right and we're pulling up. So we have a component that's pulling to the right, that's in our x direction, and then we have a component that's pulling up, which is in our y direction. So that red vector, that red force, how much are we pulling directly to the right? I'm going to call that fx. And then my blue vector, how much am I pulling up? I'm going to call that my fy. And again, that's in a standard direction, both of those. Then we're dealing with right, left, and up and down separately. So again, you'll notice that we have a right triangle here, so we can use right triangle trig. And don't freak out, again, we're just going to use some sine and cosine business here. So remember that the sine of an angle, that's my little symbol for angle, it's equal to the opposite side over the hypotenuse, op over hype. And the cosine of an angle is equal to the adjacent side divided by the hypotenuse, so the adj over the hype. And I just remember those from SineCosine. We're just using SineCosine here. So sine opposite hypotenuse, cosine adjacent hypotenuse, and then tangent opposite adjacent. We're not going to use tangent here, but SineCosine is what's leading us. So with sine and cosine, why are we doing this? I want to know what my two components are. I want to know what is fx, what is fy. I'm trying to figure that out. I was given some applied force on my hypotenuse, but I want to know what is that force to the right, what is that force up. I want to know them independent of one another. So I can just plug in some things that I know into my sine and my cosine equations. So sine of my angle, my green angle, is equal to the opposite side. My opposite side here is my fy. Opposite of the green angle is fy. And then what's on my hypotenuse? Well, my hypotenuse is how much I'm just pulling in the first place, the applied force. So my applied force is my hypotenuse. So I have fy divided by fa. Similarly, with cosine, the cosine of my green angle, again, that could be any angle, 30 degrees, 75 degrees, 90 degrees, whatever. Okay, cosine of my angle is the adjacent side, which is right next to my angle, which is fx, divided by my hypotenuse, again, which is fa. So like I said, we're trying to find what is fx, what is fy. We want to get them alone on their side of the equation. So I'm going to move fa, I'm going to multiply fa to both sides of both of these equations. I'm just showing you with the sine equation. So those FA's cancel out, and what I get is that Fy is equal to my applied force times the sine of my angle, whatever that angle is above the horizontal. So then by the same argument, the Fx is going to be equal to, because we multiplied the Fa over to the other side, it's going to be equal to Fa times the cosine of our angle above the horizontal, which is just theta, that angle symbol. So these two equations are going to be very, very helpful, not only in this unit, but also as we go forward, because like I said, these two ideas of components, the y component and the x component, can be applied to any vector. So next unit we'll be talking about these in the context of velocity. Okay, but for now, if we take a look at what does this really, how does this play out in terms of forces, why don't we draw a little free body diagram here. When I draw my free body diagram, obviously my suitcase is on Earth, so I'm going to have the force of gravity, which is pulling straight down, as usual. I'm not going to draw the normal force yet, and I'll explain why in a little bit. We have the applied force, which is going to be at an angle, how much I'm pulling it, right, straight up and to the right. So that's my applied force, and then we'll say that there's like a little bit of friction pointing back to the left. There's friction pretty much everywhere, so just a little bit of friction. And then we obviously do have a normal force because this suitcase is rolling on the ground. So there is a normal force that's pointing up. However, it's not going to be equal and opposite to the force of gravity. It's going to be smaller than that because, remember, our applied force, it has components in the x direction, or pointing to the right, and in the y direction, or pointing up. So there's a force pointing up from the applied force, and there's the normal force pointing up. So if the normal force was equal and opposite to gravity, that would mean that the object would be it would have to accelerate upwards, because also the applied force is pulling up as well. So the applied force plus the normal force is counteracting the force of gravity, which means the normal force doesn't have to work as hard. Okay, so that's just an example of how we would kind of think about these vector components on a free body diagram, okay? My Fx and my Fy, they're not real forces, so I can't draw them with like straight arrows. That's why I drew dotted lines. They're not real forces, so I can label them on my free body diagram. Just make sure that you don't draw them like you would a real force, because they're not real. Draw them with dotted lines instead, okay? So the last thing we're going to do here, I just also want to remind you is, again, we can use these same equations but plug in any vector. So my velocity in the y direction would be my velocity on the hypotenuse times the sine of an angle, and then my velocity on the x direction would be the velocity on the hypotenuse times the cosine of the angle. So those equations we'll see next unit when we talk about projectiles. And again, that angle is just 30 degrees or 15 degrees or 65, whatever our angle is. So last thing we're going to do here, just to kind of put some things into context, do a little example problem. Let's say that Miss Nielsen's pulling her suitcase with a force of 25 newtons at an angle of 30 degrees above the horizontal. Find the x and y components of the applied force. So that's my applied force at an angle. Okay, the applied force is 25 newtons. That's how much I'm pulling the suitcase. And I'm pulling it at an angle above the horizontal, which is that angle right in there. That angle is 30 degrees. So my angle is equal to 30 degrees above the horizontal. I have some force that I'm pulling to the right and some force that I'm pulling up, and I can just real quick plug and chug into those equations. My applied force is 25 newtons, and I'm multiplying by the cosine of 30 degrees, because that's my angle. If I plug that into my calculator, you have to be very careful about how you plug it into your calculator, but if I plug it into my calculator, I find that the force in the x direction, how much I'm pulling to the right, is 21.7 newtons. Now you should write to the right there. Okay, 21.7 newtons to the right. Same thing with my Fy. My Fy is going to be equal to 25 newtons times the sine of 30 degrees. Times the sine of 30 degrees. If I plug that into my calculator, I will get that the force in the y direction, how much I'm pulling up, is 12.5 newtons up. That's my Fy. So again, we're going to see more examples of these in other units, but we're in the context of forces now, so we're talking about forces in the y direction, forces in the x direction with our components. But when we talk about components, they can be applied to any vector. So today you're going to be doing some practice just breaking down vectors into their components using this method.